mesoscopic model. Okay, so and after that we'll go for like the cafeteria. Okay, so Claudio, please.
Thanks, Peter. Good morning, everybody. Yeah, the idea is just to give you some examples why mesoscopic circuits are useful to study at least complex phenomena in neuronal system. So the outline of the talk would be the following. I will give you a short introduction, analyzing a little how we model the neurons or which are the models we use. Then I will discuss two examples. The first one, it is related to anticipated synchronization, which is a phenomena that is known since 17 years already in nonlinear dynamics that we applied to neuronal circuit. And I will show you two examples, one which is the monkey cortex and the cat's primary visual system. I will arrive to some conclusions in the first part, and then I have a second example, if I have time to talk about it, which is related to signal transmission in a neuronal chain, and then some conclusions also about this part. Why study neuronal circuit? We know that neuronal circuits is relevant, or the understanding of neuronal circuit is relevant to understand the brain or the brain behavior. The structural architecture of the brain is well known, but the dynamics is less studied in general. But there are many models to study the brain, and there are different kinds of models. So I have divided it in three different, let's say, the dendrite, everything, and try to reconstruct models starting from that idea. This is too much for what I'm interested on. I want to have more general, as people working in complex systems, we are not into those details, we are more into a general aspect of the model. But there is, on the other extreme, there is a model developed by Carl Friston that proposed to use a model of perceptual inference and learning that can explain many of neurophysiological facts. This is a model that describes the brain as a whole. And this is too much for me as well, so I want to be in the middle. In the middle, there is a set of models that range from, let's say, individual neurons to neuronal population, or even a neural mass model that describe cortical columns, that are very useful to study complex phenomena in neuronal circuits. So, why using mesoscopic models? Well, we work in complex systems. In complex systems, we are interested in collective behaviors, and for that, mesoscopic models are very good. They have some advantage, as you can see there. These models are computationally less expensive than the other two I showed you before, so in general, you can run programs very easily. They contain less free parameters than other models, so in principle would allow you to qualitatively reproduce some experimental finding. So they allow us to understand the emergence of collective behaviors. And that has been proven already in aspects like coherent perception, memory maintenance, information encoding, decoding, information routing. All these aspects have been found also in models, in mesoscopic models. Of course, they are not perfect. They have several disadvantages as well. In general, they give only, qualitative results. We cannot get quantitative results from them. It's very difficult. Although I will show you some examples that if you adjust the model carefully, you might get some quantitative result. And they don't account simultaneously for many interactions that occurs in the neurons. For instance, protein interactions, neurotransmitter receptor, specific dynamics, although you can take some into account. You cannot put too many details, but even with that, the models are very good. But then you have to take into account that you have a large variety of ingredients that you can introduce in the model, and you have to decide which one you put in there. For instance, you have to know that the brain contains of the order of 10 to the 11 neurons with of the order of 10 to the 4 connection each. So it's really the most complex network that we know, and you see the variety of neurons. These are just a few examples of the variety of neurons that we have in the brain. So trying to model that is not easy. It requires some effort. There are models that describe neurons as single or multiple compartments. That means I can divide the neurons into the dendrite part, the soma, the axon. Then I have to take into account which currents are important in the neurons. And mostly sodium and potassium are always included. Chloride are also important. Calcium is important, magnesium, and so on. Then we have to know how we couple the neurons. And we can do that electrically or chemically. If we do it chemically, we have to think about slow or fast synapses, direct or indirect transmitter and receptors, we have to know the network architecture, and so on. And last but not least, we have the plasticity effect. So we have to know if we want to have a fixed connectivity between the neuron or we allow them to change in time because of the interaction. And if we do that, then there is different kind of plasticity, short-term potentiation, short-term depression, long-term potentiation or depression, and spike time-dependent plasticity, among others. So these are many ingredients we have to take into account. But I will show you that even with the simplest model that you can use, you can already predict some interesting behavior. So how to model and connect the neurons? What did we do these years? So as I said, there is a large variety of models that we can use to describe the dynamic of the neurons, and probably the simplest one is the called leaky integrated amplifier. This model describes the membrane potential of the neuron, the time evolution of the membrane potential of the neuron below the threshold. So it cannot reproduce the spiking behavior of the neuron. It only assumes that every time this potential reaches a certain threshold, there will be a spike there. But they cannot describe the spikes because it's too simple, the model. It's just a single equation. It's just one equation. There are more complete models which are two-dimensional, for instance, the Fitzwin-Agumbo model, the Morris-Lecard, or even the Iskiewicz model, which include already at least one current, usually the slow current that can be potassium, for instance. One of the most popular models, and probably the one that was used more, is the Hodgkin-Huxley model. Computationally it's a bit more complicated, but with the computer we have now, we can model it up to a few thousand of neurons. But if you have to go to larger amount of neurons, this is there is cut. Eh? Oh, vuelve a poner la presentación. No, espera. ¿Ahora? No. ¿Quieres mi conector? Sí. Eso. Ya lo he hecho. No, porque no está. No se ve, Rubén. Con el cable HDMI sí que funciona. ¿Por qué no usamos el HDMI? Con el HDMI funciona.
No se grabará nada.
Ah, vale. Pues vuelvo a intentar con el otro.
Este ordenador no tiene HDMI.
Sí que tiene. No, no tiene HDMI, no. No será en la pared, es verdad, no habrá sido en la pared.
Sí, vale, quítalo y vuelvo a ponerlo.
No mejor. Raúl, tú no tienes un cable, un conversor para el Mac. No, además está fuera de la pantalla. Gracias. Toma, Rubén. Aquí hay otro. Este es de Raúl. Uf. No es del ordenador, me parece. Yo creo que es de la pared. Es posible que sea eso. Shaking.
Pero está cortado, ¿verdad? Si metes al IFISC.
Sí, está cortado. Y está en 4/3, ¿eh?
¿Y HDMI tiene salida HDMI?
No, no tiene, no, este tiene HDMI. Bueno, si no, no lo grabes. Si funciona el HDMI, no lo grabamos y ya está, no pasa nada.
Es que no te detecta esto. Ahora.
En uno funciona.
Es lo mismo.
Y está cortado.
Bueno, y si lo...
Pon el HDMI directamente. Conecta directamente el HDMI a ver qué pasa. Ahí está, ¿no? Siempre funciona perfectamente esto.
¿Solo se verá en un proyector? Ah, bueno, y aparte no está el mando. ¿El mando del proyector? ¿El mando del proyector?
Ah, tienes que cambiar. Solo se verá en uno, espera, solo se verá en uno.
Y no se grabará.
No se grabará, pero solo se ve en uno. Y allí no. We have only one screen. How do you see from there? No. Yeah, you should move probably. Sorry. let's continue. I said all these models assume that the neurons are point object, which means that we don't describe any dendrite or soma or axon separated from the rest. So we have only a time evolution for the membrane potential, but we don't have any spatial change in the potential. As I said, synapses can be modeled either chemically. Then I will need to include a rate equation, at least a rate equation for the probability of the channels to open or close, or electrically, and in that case I would use a diffusive term, or diffusion term. Diffusive, not diffusion. In what follows, I will work mainly on chemical synapses, so we will use a probability or equation for the probability of the channels to be open or closed. So, properties of the membranes are usually described in terms of equivalent circuits. So this is just an equivalent circuit for the membrane that contains, the membrane acts as a capacitor because you have a membrane there, but it also transmits some current, so they have also some current through resistance, which here we call conductance, which is the inverse. And I am assuming here only the two main important ions that act at least in the cortex, which is sodium and potassium, and the rest is including a leaky current. And so if we use the Kirchhoff law for this circuit, the total current that flows on the circuit is the current that flows through the capacitance plus the sodium current plus the potassium current plus the leaky current that I can rewrite in this term C V dot, which is the time derivative of the membrane potential, is equal to the total current minus, and the sodium current now I write it as a conductance, which is depends on the voltage. If the voltage is small, it doesn't conduct almost anything. If the voltage is high, it's almost open the channel. So it's almost like a square function that has almost zero conductance below a certain threshold and then almost 1 above threshold. And this is multiplied by the local voltage of the membrane minus, and this is a potential which depends on the ion. It's called the Nernst potential, which is fixed, and is different from sodium or potassium or the liquid current. So this is more or less the kind of equation that we get, and these were used by Hodgkin and Huxley, and these are the two working in Plymouth Marine Lab in 1949, where they were doing experiment in this giant squid axon, and developed a model which is known as the model of the Hodgkin and Huxley model, and for that they won the Nobel Prize in Physiology or Medicine in 1963. And the model is the following. I will not enter into detail, but here they have 4 equations. The first one is the one I showed you before, which is the evolution of the voltage of the membrane, is the current which is applied to that point of the membrane, minus, this is the potassium current, this is the sodium current, and this is the leaky current. This potassium current contains a maximum conductance and a term which is n to the 4. N is the probability of a gate to be open. And this potassium channel contains 4 gates, as if I have to enter into a building and I have 4 consecutive doors. If all of them are open, I can enter. If one of them is closed, I cannot enter. So the probability is n to the 4th because I need the 4 gates to be open. In the sodium, I have 3 gates, but I have an H which represents a barrier. So I can have the 3 gates open, but I might have a barrier in the middle, I cannot cross either. So I need to have the 3 gates open plus the barrier open. This is more or less the idea behind this model, which has been used a lot. And then I have an equation for N, M, and H, which are the probability to be open or closed, which are rate equation. The first term is the rate at which these gates are open times the probability that the gate is closed, minus the rate at which it is closed times the probability that it's open. So it's just a simple rate equation. You have to solve simultaneously these 4 equations with this algebraic expression for alpha, beta of the 3 gates that has been obtained experimentally. That's what they did. They fixed experimentally this data from the measurement on the giant squid, and they get a model for the evolution of the membrane potential. With this model we work a lot. Not only us, but many people work with this model. The problem is that the parameters we know are not for humans, are not for monkeys, are usually from the giant squid. Also there are some parameters for the mammalians, but that's not so easy. That's why it's difficult to reproduce experimental findings with this model, because we have a problem of parameters to fit. So how do we model synapses? Well, synapses are in the following. We have the presynaptic part of the neuron. This is the presynaptic terminal. This is the postsynaptic neuron. So I'm connecting this neuron to this one. So an action potential is coming here to the end of the neuron, and when it arrives to the end, some calcium channels open. These calcium ions move some vesicles that contains neurotransmitters. These neurotransmitters are released here and go to the postsynaptic channels and open and attach to some postsynaptic receptor and open some channels. And this channel can be excitatory or inhibitory. So you see here the neurotransmitters are released, they go here, they bind to the receptors, and this channel can be open or not. We have two kinds of neurons, excitatory and inhibitory. Excitatory neurons promote the movement of sodium inside the cell, and when sodium enters the cell, makes the cell to spike. Because I didn't say before, but in the resting state, the neurons have a potential of minus 70 millivolts, more or less. So if you enter positive charges, this potential starts to grow, and at some point you can cross the threshold. So which means that this neurotransmitter promote excitation. These other neurons, which are inhibitory neurons, they project neurotransmitters that open chloride channels or potassium. Chloride channels are negative charges that enter, makes it more negative. Potassium are more potassium inside than outside, so when the channel is open, potassium goes out. So both makes the neuron more negative, which means less excitable. That's why these are called excitatory neurons. They project excitatory synapses, and these are inhibitory neurons. They project inhibitory synapses. So one tries to excite the other one, the second one tries to make it quiet. So let me show you the first example I want to talk about, and it came the idea that we found this paper by Brovelli and co-workers published in 2004, where they were studying the functional relation of the synchronization in the beta band. Beta band means oscillation around 20 Hertz in the brain, of neuronal assemblies in the pre and post central area of monkey cortex, as they pressed a hand lever during a waiting period of a visual discrimination task. The idea is the following. The monkey is sitting there doing a visual task and is pressing a lever. And if the cue appears, and it's the right one, it has to release the cue in less than, the lever in less than 500 milliseconds. If it does that, he gets reward. If not, he doesn't get it. So the monkey... Well, these are part of this part here. Part are motor areas, and the other part are sensory areas. Those are the areas that we're measuring. Mostly motor areas are the important for us, because it's where the monkey is waiting for doing the task. That is the area I'm going to concentrate more, motor areas. So the task is called go, no go, because the monk has either go or no go, depending on the cue that appears. And what they did, they measure from the time series, because they have electrodes implanted in these areas. They can measure the time series and do analysis. What kind of analysis they do? Well, they measure power and coherent spectral analysis of the cortical local field potential. Local field potential, to simplify, is a kind of average activity of a group of, let's say, 1,000 neurons or 5,000 neurons or so around the electrode. So this is the expression for the power spectra, which is just the Fourier transform of the time series. Then you square it and normalize it. From this, you can also define a phase. From the imaginary and real part of the Fourier transform, you can define a phase. And from the phase, you can define a time. What time? The activation time between two sites. So if I take two sites and do this, measure this time tau, I know which one activates before. That is the idea. This gives me which of the two sites activates before in terms of the phase they have. That will be important for the result they have. They also measure Granger causality. Granger causality, I will not enter into detail because the concept is easy, but the mathematics is more complicated. The idea is that if I have two areas that are connected, and if I know one of the area and can predict if activity with its own past, I do something. But if I include the past of another area, if I improve my prediction, means that those two regions are Granger causal connected. So there will be a directional influence from one area to the other if the past of one area improves the prediction of the activity of the other area. That is the idea of Granger causality. So these were the sites I showed you before. I will concentrate mainly in this part. And what they measure, I said, was coherence and Granger causality. And you see here we have red and blue arrows. Blue arrow means that we have directional influence, let's say from 3 to 1, and 3 activates before 1. That's what one we expect. If we send some information from one to the other, you expect that the first one excites and the second one follows it. This is called delay synchronization. This is the usual kind of synchronization that we know. But there are some other red arrows in which 2 sends information to 1, but 1 excites before 2. So which is it's a counterintuitive result, because I'm sending information to someone and that someone responds before receive my information. And this is called anticipated synchronization. And they were puzzled by this result, but they didn't want to enter into detail. They just said Granger causality relations were generally inconsistent with time delay values because the sign of the time delay did not predict the direction of Granger causality. So they have contradictory results. You expect that if I send information from A to B, you expect that A excites before B, and they observe the other way around. So at that point, we were working on this anticipated synchronization stuff, and we read this paper and contacted them. In particular, Steve Bressler, that was in Florida, and proposed them to do something together because we had a theory that could explain this apparently contradiction between the relative phase or the time lag with respect to the Granger causality. Why? Because as I said before, there was a phenomenon called anticipated synchronization that was discovered by Voss in the year 2000, in which if you have 2 delay coupled systems, one system ruled by the equation x dot equal a certain function of xt, and another y which is ruled by the same function and is coupled directly to the first one, and it has a negative feedback loop, then the solution xt plus tau equal to y of t is a solution of the system and can be stable for some values of k and tau. What means that? Look, this is x of t plus tau, means the future at the time tau of the variable x is equal to the value y at time t. So y is predicting the response of x in the future. And this can be proven analytically, so there is nothing here that is incorrect, and has been found in many, many different systems. So this is the idea under this. This is the typical synchronization you expect. If I have activity from here to here, I have this one, and then I have this one. What really happens in the anticipated synchronization is that I have the connection between A and B, but B evolves before does that, so the receiving population is predicting what the emitting population is going to do in the future. So how can we translate this idea of Voss to neuronal circuits? Well, the simplest is to propose a circuit composed by the excitatory and inhibitory neurons. Why that? Because we know that inhibition is already a kind of negative feedback. So instead of having, let's say, a master and a slave system connected unidirectionally, and then having an artificial feedback loop that in neurons is not so common, we decided to change this feedback loop by an excitatory connection to an interneuron, which is an inhibitory connection that feeds back into the slave. So this was our approach to explain, to study this anticipated synchronization in neuronal circuits. We used the Hodgkin-Huxley model I introduced before, so you see this is exactly the equations I showed you before. This is the connection between the neurons, which will be excitatory from M to S, master-slave. It is excitatory from slave to interneuron, and it is inhibitory from interneuron to slave. So I have actually 2 parameters here, which is the conductance of the excitation, GA, and the conductance of inhibition, GG. And then we have the synapses, which is, this is the number of bound receptors in the postsynaptic part, which contains a rate of release of neurotransmitters and the probability that the receptor is closed, minus the rate at which the channel is closed times the probability that the receptor is, or the receptive channel is open. So this is exactly what I showed you before, and this is the result we got. If we start with just having the same current to all the neurons, just making the system to spike in a regular spiking, which is a periodical one for a certain excitation and a certain external current, we put an inhibition of 20 nanosiemens here, and you see that we have master-slave interneuron. That's what you expect. First this is pulsing, then this is pulsing, and then this is pulsing. But if I change the inhibition here, what I see is that now what pulses first is the inhibitory neurons, then the excitatory, and then the interneuron. So by changing this value here, we reverse the order, this spiking after this one. And if you do changing parameters to see that this is really robust, you can see that there is a large region for different parameters. You have delay synchronization and a continuous transition to anticipated synchronization by changing the inhibitory conductance here. Certainly with this you will not convince a neuroscientist or a biologist, because these are very simple models, just individual neurons. So we say, well, why don't we try with neuronal population? So what we did is just to use what is typical recipe to model cortical population, which means having a population of, let's say, 1,000, 2,000, 5,000 neurons, containing 80% excitatory neurons, 20% inhibitory neurons, and we connected this with this certain excitatory connectivity from these neurons to this population. And in the receiver population, we also have excitatory and inhibitory, and I can play with inhibition here to try to find this anticipated synchronization regime. We use the Iskevich model, which is a very simple 2D model, which contains one equation for the membrane potential, one equation from a certain ionic channel, and some then there is a reset term. I will not enter into detail. For synapses, we include the excitatory synapses, fast excitatory synapses, AMPA and GABA-A. We use sparse connectivity and neuronal diversity in the populations. We included excitatory long-range connection and put independent Poisson input to each neuron. So we try to make it difficult. We have independent noise. Every neuron, is, when it is unconnected, is spiking at its own, so we don't have any regularity. But when we start to connect them, we start to see regularity. And this is what we see. For instance, for a certain value of the inhibition here, we see that this is the master population, which is the black one, which spikes slightly before the slave population. So this population is sending information and is spiking slightly before. This is the idea of the local field potential. The average potential of the total population spikes before the slave does. But if I change the inhibition now, I can see a situation in which the slave population pulses before the master does. But you see here, from the very beginning, the potential of the master population is higher. So it's already sending information to the slave population. And as soon as the slave population feels some information, it makes the spikes. So somehow its threshold is reduced by the interaction, by the inhibition. And you see that now this pulses before. This would explain what has been observed in the experiment by Dressler and the others. Let me just jump this because it's not important. So let me go back to the experimental data. We have this area 2 and this area 1 that we had the data, we reanalyzed it, and we will do the model for this. This is the data. This is the local field potential. The red one is area 2. The black one is area 1. And this is the coherence function, that you have a peak at which this population is oscillating. I think it's about 24 hertz. We will see later. And this is the Granger causality, which indicates that the information goes from 2 to 1. You see the peak in the Granger causality indicate that 2 is influencing 1, but 1 is not influencing 2 because the peak is very small. And when they measure the delay time, it gives minus 8.7 milliseconds, indicating that this area reaches a maximum activity 8.7 milliseconds before the other one. And these are the simulation. Here you have our time series for the master and the slave. Here master is black, slave is red. Here you see the peak in the coherence, which is in 24 hertz, as in the experiment. Certainly this is not perfect. We have a certain peak also at the multiples of this function, of this value. And here is the Granger causality. but we impose it. We impose directionality from 2 to 1, which indicates that we have to have a peak there. If we don't have a peak there, something is wrong. But you see, we get the peak, the master to the slave. We hardly have any signal from the slave to the master. There is nothing there. And when we measure the time, we got minus 8.2 milliseconds, as in the experiment. But the model allows you to play even more. So here we have some data, not only from the PNAS paper of 2004, they did some other experiment for a memory task in 2012, and they also observed anticipated synchronization. And if you see, for instance, this result would correspond to the PNAS paper where you have windows of the inhibitory conductance for which there is anticipated synchronization, and windows for which there will be delay synchronization, as in the experiment. Some areas are delay synchronized, some areas are anticipated synchronized. And in the 2012 paper, which oscillate at a different frequency, in this case 17 Hertz, we find a window of inhibition for which we have anticipated synchronization, at the 2 dots here, and there is other windows where we have delay synchronization. So we think that with this we can explain, with the change in the inhibitory conductance, we can explain why this anticipated synchronization regime appears. But the question is the only mechanism that can produce that? Well, recently we found that there might be other way to change this oscillation, this synchronization delay to anticipated. And the idea is to change the frequency of the external signal. So if I increase the oscillating frequency of the receiver population, for instance, that the Poisson rate that is receiving has a higher rate, this also produces a transition delay to anticipated. So here we have a change in the Poisson rate. Don't pay attention to the values because I will not explain why these numbers, but if you want I can explain you later. But just see that we start from an initial condition where we have delay synchronization, and if I change the external rate of the Poisson in the slave neuron, I can cross to anticipated synchronization. So what happens is that the oscillation, as soon as the oscillation in the receiver population is larger than the oscillation, or a bit larger than the oscillation in the master population, immediately the receiver puts in front its activity in front of the sender one. So this transition from delay to anticipated can be due to a change in the conductance in inhibitory neurons, or can be due to a change in the oscillating frequency of the receiver population, and we are now thinking how to distinguish between these two possibilities. Just to mention briefly, you see that if we change only the excitatory neurons in the receiver population, we see the transition, but if we change the rate in the inhibitory neurons, we don't see anything. We cannot do a transition from delay to anticipating just by changing the rate of the Poisson in inhibitory neurons. So this is the first example I wanted to show you about anticipated synchronization. Then we found another one, which I'm going to go quite fast, and was related to some measurement that Luis Martinez from Alicante was doing in the CAT visual system. The visual system of the CAT, the information enters through the retina and goes to the thalamus, which contains a nucleus, which is the lateral genicular nucleus of the thalamus. And this nucleus is very important because it boosts contrast border and increased dynamic range of the neurons, at least is what they think. But when they were recording the cells, the activity of the cells in the relay cell, which is one population in this lateral genicular nucleus, they found a slightly smaller delay time from the time it goes through an interneuron, that I will show the circuit now, than the direct time that comes, the direct path that comes from the retina. Let me show you the figure. This is the idea. This is the retina. These are the granular cells, which are part of the lateral genicular nucleus. These are excitatory neurons, and this is a group of inhibitory neurons. The information goes directly to these cells and also through this interneuron. So you see, you go here, but here you have a synapsis, and synapses always introduce delay, which makes the system slower. This is the delay time, the latency between excitatory and inhibitory, and you see that most of the excitatory times, which is the time it goes from here to here, is larger than the times going through this way. So we suspected that this could also be an example of anticipated synchronization, although the circuit is very different, because we don't have any we don't have any excitatory connection between relay cells and this interneuron here. But if you look at the visual cortex, you see these are the relay cells, these are the interneuron, and you see the connection, and this is a good circuit. And that's what he thought. This should be the circuit. But when we did simulation, for any value of the interneuron connectivity here, this inhibitory connection here, we didn't see any anticipated synchronization. We only saw delay synchronization. So we say something is wrong or we need something else into the model. But if you look at the model in more detail, you will see that there is another circuit here, which is a thalamus reticular nucleus, which is also connected to the relay cell. So the circuit also contains here another part which is very similar to our slave interneuron circuit. You have an excitation to these inhibitory neurons and an inhibition to this relay cell, which is very similar to what we had before. And if we do the simulation for certain connectivities of the inhibition, either this one or this one, we have delay synchronization, but then by changing the inhibition, mainly this one, we find that we have anticipated synchronization. Actually, he knows that the inhibition arrives before, but he didn't know if the inhibition comes from this population or from this one. So we think that what is really anticipating or making the response faster in the reticular, in this granular cells here, are this population of interneurons. And that's something that we have to check in the experiment because they didn't think about that before. Certainly with the model you can do a lot. So if you change the inhibitory in this, we're going to change the inhibition here in this branch. And you see that by changing we can go from delay to anticipated synchronization as before. And if we compare the experimental result with the simulation, we can get a very nice, this mean value of the delay synchronization is of the order of 2 milliseconds, 2.5 milliseconds, and this is what we get in the numerics, that you see that we can, by adjusting parameter, we can also get anticipated synchronization more or less with the same numbers. So as conclusion of this first example, I show that inhibitory conductance can control the delay synchronization to anticipated synchronization transition in unidirectionally coupled neuronal population. And this transition explains the observation of positive Granger causality and negative time delays observed, for instance, in monkey's cortex or the experiment in the cat's visual system. But also an increase in the firing rate on the excitatory neurons in the receiver population also leads to a transition from delay to anticipated. And that is something that we need to study more in detail because we don't know which of the two mechanisms is the dominant one. Peter, how much I have? Do I have 10 minutes? 10 minutes. Okay, perfect. So let me show you briefly the second example I wanted to show you, which is related to signal transmission in a linear chain of mutually coupled neuronal population. This is a very simple model. We just have a one-dimensional lattice of excitatory and inhibitory populations. We couple, I think it was 80 excitatory, 20 inhibitory populations, and we couple excitatory neurons bidirectionally. So in principle, it's a very symmetric configuration in which something has to happen when you connect them. To model this, we use the simplest model I told you before, which is the integrated amplifier model, which contains only a single equation for the membrane potential of each neuron in the population, which it has this term. It has a certain external bias. You can include an external constant current. It contains some external noise also, and the connectivity with other neurons. We also allows the possibility to include an external modulation to study the signal transmission. Oops, sorry. This is the condition for the reset. When the membrane potential reaches a certain threshold, you reset it to a certain value. And this is the connectivity we use for the neurons, which in this case is called electric based or current based synapses. But if we use conductor based, which is another kind, the results do not change. So we constructed 11 layers, each containing 80 excitatory and 20 inhibitory neurons, and we couple them with this condition. Each neuron receives an independent noise, a certain bias current, and can receive an external input J. Between layers, only excitatory connection is included because typically long-range connections are excitatory. When I have the population coupled, but not coupled among each other, but just the neurons inside the population coupled, the population oscillates with a frequency of the order of 40 Hz when they are isolated from the other populations. when the layers are mutually coupled, we leave them oscillating in a one-to-one locking regime. So it means we don't have period doubling or chaotic behavior. We just have one-to-one locking. To study the network response of the neuron, what we did is to inject a short current pulse to all excitatory neurons of one layer. That layer is called the host layer. So I'm injecting a small pulse just to see what happens with this pulse. And if you see, you have the oscillation, you have to decide where you put the pulse, in which phase of the oscillation. So we change the phase at which we apply the pulse, and then we see how much the next oscillation will move with respect to the appearance of this pulse. And if you see that if all the neurons have the same frequency, roughly 40 Hertz, I don't see much difference. So this pulse is not transmitted from one layer to the other one. It just dies out in the host population. But when I have one population which has a certain detuning, which means that it oscillates with a higher frequency, in this case it's only 2.5 Hertz faster than the others, you see that when I apply the pulse in this 6th layer, which is the one that is oscillating at a higher frequency, then the pulse is transmitted to the rest of the population. Which means that the appearance of a high frequency node really changes the transmission characteristic of the network. Interesting, the presence of a high frequency node also facilitates the propagation of local signals or time-dependent signals. So what I'm showing here is just we include a periodic external signal, in this case 4.8 Hertz, into the middle layer, which is layer 6, and we study the response of the other layers, how they respond at the frequency of the external signal, 4.8 Hertz. And you see, here I'm plotting the response of the populations. Here I'm plotting the detuning, which means the different frequency between the high frequency node and the other nodes. You see that about 5 or 4.8 Hertz, we have a maximum response of almost all the layers, which means that if I have a detuning of the order of 4.8 Hertz for these parameters, we have a better propagation of the signal all along the network. But this is not a resonant effect. We checked that. Actually, the lowest the frequency of the external signal, the better it propagates into the linear change. So this is not a resonant effect. It is more interesting to see what happens when we have two signals. What would happen if we have two signals? If I apply one signal to the high frequency node and some other signal to another node. So it is interesting to see that when we apply a high frequency signal to the, a signal to the high frequency node, in this case is node number 5, and I applied another signal with a different frequency to node number 7, you see that the signal applied to node number 5 propagates to both sides of the chain, while the signal applied only to the regular node, which is oscillating at 40 Hertz, which is node 7, only propagates to the right. It cannot propagate to the direction of the high frequency node. So somehow this high frequency node is blocking the signal that is coming from the other node. What would happen if I have a more complicated situation, not just a linear chain? What happens if I have like a hub and a linear chain here, and I have a star-like configuration here, and I can have the 6th node to be the high frequency node, or I can have, for instance, the 8th node to be the high frequency node. So if the high frequency node is the 8th, and the signal applied to this node for a certain value of the detuning, which here is 7.3, it doesn't matter, you see that the signal propagates very well both to the star and to the linear change. However, if the high frequency node now is number 8, and I have here the other node, which is the number 6, the frequency applied to the hub can only propagate to the star. It cannot propagate to the linear chain because the high frequency node is blocking. So this hub that usually is assumed to be very good to sparse information can be blocked by a dynamical node. So it doesn't mean that the hub is always a good node to transmit information, because the dynamic of another node can block this transition, as you see here. here you see that the signal in this hub, which is a normal node, and this is the high frequency node, these signals only propagate to the start, to the left side, but it cannot propagate to the right side because of the presence of the high frequency node there. So just to conclude, high frequency node seems to play the role of a source, being highly influential for the activity propagation, despite the symmetric, homogeneous structure that we have studied. Because the first case at least was a linear chain, which was very symmetric, and still this high frequency node is introducing an asymmetry in the system. These results were confirmed by measuring the network response as well as the mutual information indicator. So we also study if mutual information reflects the same that we see with the signal. The intrinsic firing rate across neuronal population may thus determine preferred route of communication or signal transmission. And this can be easily controlled by changing the frequency of the layer. So just by changing the frequency of the layer, we can change the connectivity of the network, or what is called the functional connectivity of the network. So that's all I wanted to tell you. Just let me thank the people that have been working in this aspect with me. Steve Bressler from Florida, Santiago Canal from the Instituto de Neurociencia Alicante, Pedro Carelli, Mauro Copelli from Universidad Federal de Pernambuco in Brazil, Leonardo Dalla Porta and Cristian Estarelias here in IFISC, Fernanda Matias in the University of Alagoas in Brazil, Aref Parisi and Alireza Balizadev from the Institute for Advanced Study in Basic Science in Iran. Thank you very much for your attention.
Thank you, Claudio. Questions?
How many times can they do the experiment with those poor beings before they?
How many times can do the experiment of?
Yeah, with the animals.
Well, the monkeys were two monkeys.
But how many times can they do the experiment with the same animal?
They are running for a long time.
They do not die. I mean.
No, not at all. They live for 10, 15 years easily.
And with the cats?
The cats, no.
The cats. So
the cats not, because they are anesthetized. They are anesthetized and then they are killed.
How do they measurement with the monkey and with the cat? With the
both were electrodes. Both were implanted electrodes. Different kind of one were implanted in the cortex. That's why the monkey they run through a surgery. They are implanted and then they can live with the implant forever. I mean, until they die. They don't die because of the electrode. They just die because they got old or they had an infection or whatever.
And
but they don't die because
the cat was.
The cat is different because then you have to do it open, with the brain open. Then you have to put in the thalamus, which is a nucleus which is down in the brain, and then they die after that.
If they do the experiment with the monkey and they try to measure a single spike,
they can do single spikes as well.
But
yes.
The monkey didn't die in that case.
No. They can do both. They can have electrodes that record single spikes, or they can have electrodes that record local field potential. Same electrode sometimes can measure parts of locally single spikes, and they can measure local field potential. And they don't die. I mean, sometimes
I saw a similar experiment, and they used monkeys, and they wired the brain of the monkey to make the measurement, and the monkey just can do the experiment like 6-7 times, and then.
No, this was not the case.
I don't see the difference because
I saw 2 times experiments in monkey, one in Germany, in the group of Wolsinger, one in Natal in Brazil last year, and in both cases monkeys are alive there. I never seen sacrificing a monkey after 6. I don't think people would do that.
Okay.
At least.
Very interesting results. One very fundamental question. You introduced in the beginning anticipated and lax synchronization as 2 different solutions. And then you show in your results that you have a continuous transition from one to the other. What does it mean? Are those 2 mathematically different solutions?
No.
Or is it the same one? So does therefore even the time t equals 0 doesn't have any physical relevant roles? Or is it just a continuous transition of the same solution?
I would say that it's a continuous transition of the same solution, because you can get, actually when we included plasticity in the neurons, we got more zero lag synchronization space. which indicates that the transition was still continuous from delayed to anticipated, but in my opinion, it's only a lag synchronization, which can be positive or negative, but for me, it's the same mathematical solution.
Interesting, because in other dynamical systems, it seems to be different ones. So,
well, for us, it was important to find this continuous transition because we are working in a periodic regime. So if you don't find a continuous transition and working with a periodic regime, you cannot ensure that you have a change from delayed to anticipated. It can be always delayed because you can just jump one cycle.
Yeah.
But this was, at least what we found, was not the case. Then in population it's different because there you have, it's not so periodic. You can, it's still periodic, but the local field potential is not the same every cycle, so you can distinguish if you are changing one cycle or not.
And a very short question to the last part, where you discussed the role of the high frequency nodes to, for example, control the transmission or the propagation of the signals. In electrical systems, usually this happens when you have an impedance mismatch, right? Can this, what you see here, the dynamical effect, also be understood in terms of an impedance mismatch?
I think so. I mean, there is nothing particular in this chain that would not occur in other circuits like electric circuits or oscillators. Or, I mean, we just found it here because we were studying this chain of neurons. But I'm sure that it is much more general than this. It could appear in. I don't know if I'm not so expert in these things of impedance mismatch, but we can discuss that. But I think it should be general. This should be.
Any other question?
Sorry for the question, because it does mean that I didn't pay attention through all the talking. But what this is this Poisson rate exactly that you vary?
That's important. It's an important question. Why do we put Poisson rate? Because when you measure the activity of a neuron experimentally, just let's say an individual neuron, and you draw the interspike interval, you get a Poisson distribution. So that means that this neuron is subject to a noise from other neurons, from activity from other neurons that is feeding it. So the way to include that in the model is I say, well, I'm taking a population, but I have so many other neurons that I'm not considering. How do I consider that? Well, I consider that by including some Poisson rates, some Poisson trains. Into each neuron is receiving many different Poisson of many other neurons that I'm not putting into the population. That is the idea, to include a Poisson train there. It's a good question.
More questions? Okay, so if not, we thank Claudio again.
Thank you.